Welcome to the UGC lecture series. This is the PG Pathashala lecture series on computer science and we are talking about the paper machine learning. In this module we are going to discuss belief networks. This is not the first time we are talking about Bayesian belief network. We had already given an introduction in the previous module. In this module we are going to go a little more into detail on Bayesian belief networks. So now let us look at the people responsible for the creation of this module. These are the people involved in the development and creation of this module. And these are the learning objectives of this module: to understand the design of Bayesian network, to understand the examples of Bayesian network. More, we have seen some examples in the previous module also. Here we are going to go into a little more detail about these modules and these networks, and to explain inferencing in Bayesian belief networks. Okay, how inferencing is done. We are not looking at the algorithms, and some of the keywords are Bayesian belief networks, conditional independence, joint probability distribution, and causal and diagnostic inferences. So, let us now look at how to construct Bayesian networks. So, constructing of a Bayesian network, the first step is you have to choose an ordering of the variables. So, what are the variables you are going to consider and what is the ordering of the variables? What do we mean by ordering of the variables? Which is dependent on which? So, let us assume that we are choosing the variables x1 to xn. In the next step, for each of these variables, we have to add this variable to the network. Okay. So, you have to select the parents of x1 to xi minus 1. So, from and such that the probability of the xi is dependent on the parents of the probability of xi is dependent on the given the parents of xi, you can find the probability of xi. So, that means p of xi is equal to given xi to xi minus 1, and the choice of parent guarantees that this given the probability, if you want to find the joint probability distribution of x1 to xn, then it is given by the product of I is equal to 1 p of xi x1 to xi minus 1, which is the chain rule, and the p of xi given the parents of xi by the construction rule. So, this is the construction of the Bayesian network, and how it is how the ordering is decided, what are the variables, how the ordering is decided, how you decide on the parents, and how the choice of the parents guarantees that you get this joint probability distribution. So, let us take a simple example again. So, we are going to look at these examples again and again to understand the concept. So, the Bayesian network, we are taking a very simple example of just two nodes, smoking and cancer, and it is given that yes, here smoking can take three values. We are moving a little away from Boolean. So, it can be smoking no, light, heavy, and cancer also can have three values: none, benign, and malignant. Now, S has no parent, so what you have is a probability of S, it is not dependent on any other variable, but C is dependent on S. So, you have probability of C cancer given smoking. So, this is what is the simple two node Bayesian network. Remember, both the nodes can take on three values. Now, first we will talk about the probability of S smoking. So, it is given that among the probability of yes having a value no is 0.80, having a value light is 0.15, and having a value heavy is 0.05. This is given by the domain expert, we are not calculating anything. Next we have to find the probability, conditional probability of cancer given smoking. So, that is P of C given yes, and that is given by, now smoking can be no, light, and heavy. So, the probability of C being none, no cancer, when there is smoking is no, the probability is 0.96, the smoking is light, it is 0.88, and probability heavy it is 0.60. Now, C is equal to benign, then if the smoking is no, you have probability 0.03, light 0.08, heavy 0.25, and if it is malignant, smoking no, the probability is 0.01, light it is 0.04, and heavy is 0.15. Again, this conditional probability table, as it is called, is given by the domain expert. So, you have two tables associated with these two nodes. Either it can be a independent probability table, in which case that particular node does not have a parent, or it is a conditional probability table if the node has a parent. So, this is the first step. Now, I want to find the probability of joint probability of cancer and smoking. So, that is given by the probability of cancer given smoking into the probability of smoking. So, that is given, this is the probabilities of no light heavy given none. So, this we have just multiplied these two values. If you can see 0.96 into 0.80 gives you 0.768, 0.88 into 0.80 gives you that values. So, this is nothing but the calculation, this is giving you the probability of C comma S given the probability of C S into probability of S, which you have with you. This is the product rule. Now, you have talk about marginalization. So, here we want to do some little bit of normalization. So, here what we have done is this particular table we have not done anything extra except that we have calculated a total. So, you see that 0.768 plus 0.024 plus 0.008 is 0.80 and so on the column and so the bottom. Now, what we do for marginalizing, we divide each value by its maximum value, total value. So, you have 0.768 divided by the 935 that comes here, 0.024 divided by the 0.046 and this. So, if you do this, if you cancer non-benign malignant, you will get the values, the division values will give you these values. So, this is the final Bayesian rule. So, the Bayesian rule, now if you want to find out S smoking given cancer, what is the probability of smoking given cancer? This is nothing but the probability of C given S into P of S divided by P of C, that is the probability, but that term is nothing but the joint probability of P comma C comma S divided by point C, probability of C, which is what we have done here. So, C the probability of C comma S is given here and then we have divided, that is we have divided this by the total probability of cancer value, which is what we got as 0.935. So, this gives you the probability of S, the probability of S given cancer is none, the probability of S equal to no given cancer is none, probability of S equal to benign. These values are different from this, right. This is the probability of cancer given smoking and we are finding out the probability of smoking given cancer. What is the probability of smoking given cancer? This is the Bayesian rule. So, we have played around quite a bit. With just two nodes we have found the, given the probability of smoking, the conditional probability table of cancer given smoking, we have found out the joint probability of C and S, the probability of S given C. So, this is what we have done, that is smoking given cancer. So, now let us look at causes and Bayes rule. Okay. So, now let us look at a small example again. We have here rain and wet grass and now suppose you are given rain, the direction of the arrow is what we are talking about, parent. So, given the parent, what the probability of wet grass is called causal and given wet grass, what is the probability, what caused that wet grass is diagnostic. Now, you would be given two tables associated with the two nodes. So, R does not have any parent. So, you have a individual probability, independent probability, P of rain is equal to 0.04. So, obviously, P of not rain is 0.6. Now, you have wet grass. In wet grass, you have probability of wet grass given rain is 0.9. So, probability of wet grass given, so probability of not wet grass given rain is 0.1. The next is probability of wet grass given not rain is 0.2. So, probability of not wet grass given not rain is 0.8. So, that calculation, so it is actually a 2 by 2 table. So, he is just giving you two values, the other is automatically found out because it is equal to 1. So, this is given to you. So, you are given the conditional probability table and the independent probability of the two nodes. Now, the causal inference we have seen before. What is this diagnostic inference? Knowing that the grass is wet, what is the probability that rain was the cause? This is what is diagnostic inference and this is not as straightforward as causal inference. So, let us look at how it is. So, probability of rain given that it is wet grass is by Bayesian rule, probability of wet grass given rain, this is just an application of Bayes rule, probability of wet grass given rain into probability of rain divided by the probability of wet grass. Now, that can be rewritten as probability of wet grass can be rewritten as probability of wet grass given rain into probability of rain plus probability of wet grass given not rain into probability of not rain. So, this is a, we are replacing probability of W, probability of wet grass by two terms where you have probability of wet grass given rain and the probability of rain, probability of wet grass given not rain and the probability of not rain. So, with this values, now probability of wet grass given rain is 0.9 into probability of rain is 0.4, that comes there, probability of wet grass given rain is 0.9 into probability of rain is 0.4 plus probability of wet grass given not rain is 0.2 into probability of not rain is 1 minus 0.4, 0.6. So, the probability of rain given wet grass, that is your diagnostic inference, is 0.75. So, this is a diagnostic inference, not straightforward, it is inference, but we are not using any algorithm to do this, it is a simple case. Okay. Now, let us take some example and see how it is decided, how you draw the Bayesian belief network. Now, let us take a story. We have Inspector Smith is waiting for Holmes and Watson, who are both late for an appointment. Now, Smith is worried that the roads are icy and one or both of them may have crashed the car. Now, suddenly Smith knows that Watson has crashed, some knowledge, he gets a phone call probably. Now, Smith thinks if Watson has crashed, probably the roads are icy and there is every chance that Holmes also will crash. Now, he gets a new information that it is warm outside and the roads are salted. So, there is no probability of sliding or whatever is less. So, Smith thinks Watson was unlucky, Holmes should still make it. So, now how do we draw this as a Bayesian belief network? So, you have state of roads, now first you have to decide on the variables. So, state of roads, Watson having a crash and Holmes crashing. So, state of roads, there are two possibilities, icy, not icy, Watson crashing, not crashing, Holmes crashing, not crashing. These are the three possibilities, Boolean. Now, you are suddenly given information, this is the probability Bayesian network with the dependencies specified. So, here we are just saying that arrival is not important, state of roads is icy, there is a possibility of crashing, that is what we are saying. Now, suddenly we get information that evidence that Watson has crashed. So, when Watson has crashed, you have the flow of information that Watson has crashed. This makes the states of roads icy to have a more probability, and in which case Holmes crashing also has more probability. This is the flow of direction. Now, we have another evidence where we have that the state of roads is not icy. Therefore, the flow of information is again in this direction, but here the probability of Holmes not crashing is larger. Now, let us take another example. This is a famous example that is used for most of the Bayesian network explanations and so on. This was given by Julia Pearl. So, you have a new burglar alarm installed at home. It is fairly reliable in detecting a burglary, but unfortunately it also responds on occasion to minor earthquakes. So, burglary happens, it is good, and you can also have minor earthquakes. Both cases it sometimes responds the alarm. Now, you have, that is one situation. Then you have two neighbors, John and Mary, who have promised to call you at work when there is an alarm, when they hear the alarm. So, John always calls when he hears the alarm, but sometimes confuses telephone ringing with the alarm ringing. So, sometimes when he calls you up, you do not have to believe that, it is a belief network, believe that actually the alarm has rung, because it may be a telephone ringing. Mary on the other hand likes rather loud music, and sometimes they may miss the alarm altogether. Look at the two examples, two situations. John will call unnecessarily, Mary may not call when it is necessary also. Given the evidence who has called or not called, you would like to estimate the probability of a burglary. So, this is the problem. So, the first step is determine the variables, what are the random variables that should be there, and then you have to determine the causal or some type of influence relationship in order to develop the Bayesian network, topology of the network. So, in our example the variables are burglary, earthquake, because both cause an alarm obviously, and John calling and Mary calling. So, these are the 5 variables, and the network topology reflects the causal knowledge, can set the alarm, an earthquake can also set the alarm can cause Mary to call, the alarm can cause John to call. So, here you have alarm due to burglary and earthquake, and the alarm can cause John and Mary to call. So, this is the topology of the belief network, very simple topology. Now, the next step is you have to specify a conditional probability table or the CPT for each node. Okay. So, each row in the table contains a conditional probability of each node value for a conditioning case, possible combination of values for the parent nodes. In the example, the possible values of each node are true or false only. So, it is a Boolean. The sum of the probabilities of each value of a node given a particular conditioning case has to be 1. This we have already discussed in the module previous module. So, here we have, for example, this the conditional probability table for the alarm node. So, the alarm, if you see the diagram, the alarm is dependent upon two parents, burglary and earthquake. So, the conditional probability table will have burglary and alarm. So, burglary and earthquake can be true, one can burglary can be true, earthquake can be false, burglary can be false, earthquake can be true, and both can be false. Now, the probability of alarm given burglary and earthquake. So, if there is a burglary and an earthquake, the chances of the alarm ringing are 0.950, probability of alarm is 0.950 and false is 1 minus that. If the burglary is true and the earthquake is false, this is the probability 0.95040 and 0.60060. False and true 0.290710, and false and false, the probability of alarm going is very small, not 1, and not going is 0.99. If you see the rows, each row will add up to 1. So, this is what is given. Burglary, probability of the burglary is 0.001. So, the probability of no burglary is 1 minus that. Probability of earthquake is 0.002 and 1 minus 0.002 is the probability of no earthquake. Then alarm, we have already explained that in detail. Now, John is dependent only on upon alarm. So, alarm can have true or false. So, if the alarm is true, the probability of John calling is 0.90. If the alarm is false, there is also a probability of John calling because he hears a telephone ringing. So, it is 0.05. Mary calls is again dependent only on one parent alarm. So, if the alarm is true, the probability of Mary calling is 0.70 because she can miss because she keeps loud music. The probability of her alarm false and Mary ringing is also quite low because she won't do that. She won't hear a telephone and do that is a characteristic given to us. So, if you look at this, the building of the topology, deciding on the topology of the Bayesian network is quite important. These are all given by domain experts. Once this is given, this is the Bayesian network. Okay. So, we will come back to this again. Now, another example is a population wide anomaly detection assessment called PANDA. This was till now we have looked at toy examples. So, this was a detector specifically for a large scale outdoor release of inhalational anthrax and uses a massive causal Bayesian network. So, this is one of the initial uses of a massive Bayesian network. So, this is called a population wide approach. Each person in the population is represented as a sub network of the overall model. So, the global nodes is the anthrax release, and you have a location of release and time of release. These are called as interface nodes in this example, and you have the person model. Note the conditional independence assumptions. Anthrax is infectious and not non-contagious, and the structure designed by expert judgment, and parameters obtained, the parameters for the person, everything is obtained from census data, training data, expert assessment by literature and experience. This is another example. Now, let us go back to the distribution story we were talking about. So, given n variables, we want to find the probability distribution of all the variables x1 to xn. This is nothing but a product of the variable, the conditional probabilities of a xi given the parents of xi. So, for example, here we have taken probability of John calling, Mary calling, alarm being there, no burglary, no earthquake is given by from the figure. Probability of John given the alarm, probability of Mary calling given the alarm, probability of alarm ringing given not, you have to take the values there. So, not burglary, not earthquake, and probability of not burglary and not earthquake. So, all these variables are the values are directly available in the table. So, for example, John calling given alarm and so on. So, this is the variable, and you have a probability of the, that is John calling, Mary calling, alarm ringing, and no burglary and no earthquake. Obviously, from the diagram example by now you will know that it has very low probability. So, you get the value like this. This is directly from the tables given. Now, before we go further, let us look at some conditional independence in Bayesian networks. So, there are three types of connections that are possible in a Bayesian network. One is a serial connection. So, we are just given an example, visit to Asia, tuberculosis and chest x-ray. So, knowing tuberculosis makes A and X, visit to Asia and chest x-ray independent. So, this is called an intermediate cause. Next we have diverging, it is given I mean you have smoking as the parent and lung cancer and bronchitis as children, knowing smoking makes lung cancer and bronchitis independent. So, this is called diverging connection. Then you have converging connection, that is lung cancer and bronchitis you have dysentery, yeah, and knowing D or M makes either this or that, makes L and B, that is lung cancer and bronchitis independent. This is called the common effect. So, you have the common cause, common effect and then intermediate cause. These are three types of conditional independence. Remember, Bayesian network is basically based on conditional independence. Now, let us look at semantics of belief networks. A belief network is a representation of the joint probability distribution of a domain. Joint completely specify an agent's probability assignments to all propositions in the domain. So, it is both simple in one way and complex in another way. Now, let us look at calculation of the probability of the event that the alarm has sounded. We are just wording it, we have looked at this before. Probability that the alarm has sounded, but neither a burglary nor an earthquake has occurred, but both Mary and John called. So, you have to take each variable and give the values. So, the alarm has sounded, so A is true. Neither burglary nor earthquake, so not of burglary, not of earthquake, and both John and Mary call. John, so John is true and Mary is true. So, that calculation we have already discussed. This probability is very low. Now, as we already seen, this network is a representation of the joint probability. So, this is what we have. Each entry in the joint is represent the product of the appropriate terms of the conditional probability distribution in the belief network. So, that is how you calculate this. So, the view 2 is encoding of collection of conditional independence statement. John call is conditionally independent of other variables in the network given the value of alarm. So, if you are given alarm, John and Mary calling are independent, and earthquake and John is also independent of earthquake occurring or burglary occurring. This is the semantic viewpoint of how a joint distribution becomes simpler because of these conditional independence assumptions. Now, let us look at the other thing, causal inference. Inference basically diagnostic and causal inference. So, inference from cause to effect, given a burglary, what is the probability of John calling? You given a burglary. So, that was a joint probability distribution of the whole network. Now, we are taking specific cases. We are given that John is probability, what is the probability of John will call you when a burglary occurred? So, the probability of John given B. How do you find out that? The probability of, first before you do that, you have to, because John is dependent on alarm, the probability of alarm given burglary is what you have to first find out. So, that is nothing but probability of burglary and probability of not earthquake into 0.94 plus probability of burglary plus probability of earthquake into 0.95. So, how did you get this? Let us look back. So, this is the one. So, you have probability of John, we wanted to find probability of alarm given burglary. So, burglary is given. So, burglary is 2 truth values you have to take 0.9 and probability of burglary given earthquake is true and probability of burglary given earthquake is not true, both you have to consider. That is why you have 2 terms there. So, let us look at that a little more in detail. So, those are the 2 terms there. So, probability of burglary into probability of not earthquake is into 0.94, probability of burglary because that is given, probability of burglary given a burglary. So, probability of burglary into probability of earthquake into 0.95 which we got from the conditional probability table. So, that is nothing but 0.94. Now, the probability of John calling given a burglary is dependent upon probability of alarm going off into 0.9 plus probability of alarm not going off into the probability. This is again given to us. So, that is equal to 0.94, that is probability of A given B 0.94 into 0.9 plus 1 minus 0.94 0.6 into 0.95. So, you get 0.85. So, the probability of John calling when there is a burglary is 0.85 and similarly you can calculate probability of Mary, A and B remain the same, that value is same 0.94. So, that is what we have found out, but probability of Mary calling given the burglary is 0.67 in using similar calculation. So, this is straightforward calculation. Now, let us go to So, this is given here. So, you can find out that. So, probability of B is 1 because we know the burglary is there. 0.998 is the probability of we have calculated those values and this is what you get. Now, let us go to the other one. Now, given burglary, what is the probability of John calling, but burglary does not directly affect John. So, you first have to find out what affects John, which is alarm. So, probability of alarm given burglary, and after you do that you have to find out, given that probability that alarm has occurred, what is the probability of John calling. So, now the next one is from effect to cause. Given that John calls, John has called. Previously we had burglary has occurred, what is the probability of John calling? Here it is a diagnostic one. Given that John calls, what is the probability of burglary occurring? So, probability of burglary given John has called is given by probability of, this is a Bayes theorem again, probability of John calling given burglary into probability of burglary divided by probability of John calling. So, what is Pj? We have not given that value. For that we need to know Pa first. So, Pa is nothing but probability of alarm is probability of burglary into probability of earthquake into 0.95 plus probability of not burglary, 4 terms you have, that is all the 4 terms you have to consider for the probability of alarm, because 1 minute, probability of alarm is determined by both probability of burglary as well as probability of the earthquake. So, all the 4 values, burglary occurring, not occurring, and so 4. So, that is why you have those 4 values there. From that you get a point probability of A, this is 0.00257. So, probability of John calling, which we want to find out, is probability of A into 0.9 plus probability of not A into 0.05, which is 0.00257, minus that you get this value. So, you get probability of John calling as 0.052. So, the probability of the burglary occurring given John calling is 0.85, which we found on the previous case, into 0.01 probability of burglary divided by the probability of John calling. So, you get 0.016. So, the probability of John calling and a burglary occurring is not very high. So, there are many false positive. This is a diagnostic inference. So, we have explained the design of Bayesian networks, how given a problem you can design a Bayesian network. Then we have discussed the examples of Bayesian networks and illustrated inferencing, both causal inferencing and diagnostic inferencing in Bayesian belief network using examples. These examples are small examples. If you want to actually do this for large networks, we need an inferencing procedures which are there. We have not discussed that, and that is not within the scope of this particular course, so paper. So, thank you.